Hi, I'm Adnan Akbar, MPhil in Physics and BS in Mathematics. And today I am here again with my YouTube channel named Real Physics. And today our lecture number is 6, in which we will discuss electric field problems. Actually, these are most important problems. And we will move from basic to advanced. And you will get training to solve some complicated problems of an electric field, which will help you in some important exams. So let us start without delay. Our first problem is two charges of 1 microcoulomb and -2 microcoulomb are separated by a distance of 2 centimeter. Find the electric field at a point exactly mid of the line joining, and according to the given data, Q1 is equal to 1 microcoulomb. And one thing that you should keep in your mind, always whenever we will solve the problem, we will change the given unit according to SI units. So here we have to change micro to coulomb and centimeter to meter. So Q1 is equal to 1 cross 10 raised to minus 6 coulomb, and Q2 is equal to -2 cross 10 raised to minus 6 coulomb. And the distance between these two charges is 2 centimeter, which will become 0.02 meter. And the distance of each charge from the midpoint is 0.01 meter, and the Coulomb constant that we will use here in these relations is K is equal to 9 cross 10 raised to power 9 Newton meter square per Coulomb square. In the diagram, you can see these charges have opposite nature. So we can say the direction of electric field of both charges will be similar. So according to the superposition principle, net electric field at the midpoint will be the sum of these two fields E1 and E2. So E net is equal to E1 plus E2. And after putting the formulas of each, our relation will become K multiplied by Q1 over R square plus K multiplied by Q2 over R square. K has the values 9 cross 10 to the power 9, and Q1 has the value 1 cross 10 to the power minus 6 over 0.01 whole square, which is the distance of Q1 from a midpoint, plus 9 cross 10 to the power 9 cross 2 cross 10 to the power minus 6 over 0.01 whole square, which is also a distance of charge 2 from the midpoint. After simplifying it, we have the final value for the net electric field is equal to 2.7 cross 10 to the power 8 Newton per Coulomb. And let us move towards our next problem. Find the net electric field at the charge on the vertex in the given diagram. Given diagram is actually an equilateral triangle ABC, and three charges are oriented at its corners as shown. Each charge has the same magnitude and they are equidistant from each other sidewise. And we have to measure the net electric field due to A and B at vertex C. And for that purpose, we have to measure EBC and EEC to calculate the net electric field. And one thing more that I have to clear, that the electric field on C due to A and the electric field on C due to B both will have same value because they are equidistant from C, and all the charges have the same magnitude. So ECB is equal to KQ over A square is equal to ECA is equal to E. And let us apply the law of cosine to calculate the net electric field at the vertex C. Our relation will become ER is equal to square root of E square plus 2 E dot E cos of 60 degree. And cos of 60 degree will result value 1 by 2. Then our relation will become ER is equal to square root of E square plus 2 E dot E by 2. And in this equation, 2 will cancel the 2, and our relation will become ER is equal to square root of E square plus E square plus E square. And after combining it, ER is equal to E square root of 3. And from equation 1, we know the value of E, KQ over A square. So our relation for the resultant electric field or the net electric field at the vertex C is ER is equal to square root of 3 multiplied by KQ over A square. and the direction of this net electric field will be ER as shown in the diagram. Let us move towards our next problem. We have a sphere shape in which charges and length distribution is shown in the figure. Find the electric field at minuscule charge at point D. So we have sphere shape as shown, and we have to first analyze it. Then we will move towards solving this problem. Here is a sphere shape ABCD at 4 charges having the same magnitude are oriented at its corner, and 3 of them have same nature while one of them has opposite nature, which is at D as shown in the diagram. As we have to calculate the electric field at point D, then first of all we need to know how many charges are applying their electric field at D. So here one charge B is applying electric field at D, other charge along the diagonal is applying electric field from E to D, and the third one from C to D. And we have to calculate the net electric field at D due to these 3 electric fields. For that purpose, one thing that I need to clear, the field from B to D and the field from C to D will have same magnitude because they are equidistant from the charge D, and they have the same magnitude. So the net electric field according to the superposition principle is equal to ECD plus EBD plus EAD. EAD is actually the electric field along the diagonal, while ECD and EBD are the electric field which are perpendicular to each other as shown in the diagram. If they are perpendicular, then they can provide some resultant ER. Then our relation A will become E net is equal to ER plus EAD. In this relation, it is clear that we have to measure the resultant electric field ER due to B and C and electric field along the EAD to solve this problem to find the net electric field at D. So first of all, we have to solve the resultant electric field due to B and D. From the diagram, as I have cleared earlier, ECB is equal to EBD is equal to E, and ECD and EBD are perpendicular fields. So let us apply the law of cosine. Law of cosine will show ER is equal to square root of E square plus 2 E dot E cos of 90. And you know cos of 90 is equal to 0. So then our relation will become ER is equal to square root of E square plus E square, and our relation will become, after simplification, E square root of 2. And value of E we know KQ over A square. Then our relation final for the resultant will become ER is equal to square root of 2 multiplied by KQ over A square. Now we have to find the value of electric field along the diagonal. For that purpose, we need to know the length of the diagonal, which is A square root of 2. Then our relation for the diagonal electric field EAD is equal to KQ over A square root of 2 whole square is equal to KQ over 2 A square. From equation 2 and 3, we can say we have calculated the resultant electric field and electric field along the diagonal. Then we have to replace these values in our main equation to find the final results. E net is equal to square root of 2 multiplied by KQ over A square plus KQ over 2A square. And in this relation, you can see KQ over A square is common. So by taking common, our relation will become KQ over A square into square root of 2 plus 1 by 2. Actually, this problem is a training to solve the complex problem. In those complex problems, the values of Q1, Q2, Q3 and Q4 will be given, and their mutual lengths will also be given. Then you need to solve those problems likely. So let us move towards our next problem. Where should we place a charge along the line joining two similar nature charges so that the net field will be 0 on it? Let us solve and discuss this problem by using two cases. First of all, we consider we have two charges q and plus 4q are separated by length L, and you can see these are similar in nature. And consider we have to place the third charge in its surrounding, and we will check the net electric field will be equal to 0 or not 0 at that point. In the given diagram, you can see Q will apply a force on the third charge Q, which will be of repulsion, and 4Q will also apply a force which will also be of repulsion. Then charge will not be in equilibrium here, and the net electric field will not be equal to 0. So this case will not work. Let us move towards our second case. In this case, we can see a third charge is placed closer to the smaller charge in between these two given charges. And here we need to analyze that net electric field can be 0 or not 0. As both charges have the same nature, so if one charge will repel, then other will also repel. And it is possible that at somewhere in between two of these charges, we can find 0 net electric field point. So for that, we have a condition: electric field due to smaller charge E1 should be equal to the electric field due to bigger charge E2. So KQ over R square is equal to K4Q over L minus R whole square. K will cancel the K and Q will cancel the Q, and our relation will become 1 by R square is equal to 4 over L minus R whole square. Taking square root, our relation will become 1 by R is equal to 2 by L minus R. L minus R is equal to 2R, and after simplification we have the relation for R is equal to L by 3, which is showing in such type of the cases we need to place the third charge closer to the smaller charge at a distance 1/3 of the total length. And to solve such type of problems, we also have a shortcut, which is actually a formula. X is equal to square root of Q1 over square root of Q1 plus square root of Q2 into L. And to verify this formula, again we consider we have a charge Q1 is equal to Q and Q2 is equal to 4Q. And let us replace these values in the formula. X is equal to square root of Q over square root of Q plus square root of 4Q into L. Square root of Q will cancel to the square root of Q, and our relation will become X is equal to 1 by 3 into L, which is similar result to our previous problem. And let us move towards our next and last problem of this lecture. Place a charge on the line joining two opposite charges so that net electric field acting on it will be 0. It is similar to the previous problem, but the only changing that here the charges are opposite in nature, while in our previous problem charges were in same nature. So again consider we have two charges Q and minus 9Q, which are separated by a length L, and we will solve this problem by discussing two cases. First case, if we will place the charge in between them, then what will happen? In the diagram, you can see both charges have opposite nature. Then the electric field applied by the smaller charge on the Q will be of repulsive nature, and the electric field applied on the third charge by the bigger charge will be of attractive nature, and third charge will not stay in between them, and there will be no 0 electric field point in between them. So this case will not work. And let us move towards our second case. In this case, we will place third charge in the surrounding of two given charges. So we have placed the third charge closer to a smaller charge, but in its surrounding. And distance of some third charge from the smaller charge is R, and the distance of third charge from the bigger charge is R plus L. For electric field to be 0, we have a condition: the field applied by the smaller charge should be equal to the field applied by the bigger charge, and both these fields should be in opposite direction. This case will work. E1 is the field applied by the smaller charge on the third charge Q, and E2 is the field applied by the bigger charge on the third charge Q. kq over r square is equal to k 9q over L plus r whole square. K will cancel the k, q will cancel the q, and our relation will become 1 over r square and 9 over L plus r whole square, and taking square root, our relation will become 1 over r is equal to 3 over L plus r. After simplifying it, L plus r is equal to 3r, and our relation for the r will become r is equal to L by 2, which is showing in this case we need to place the charge at a length half of the total length on the left side of the smaller charge as shown in the diagram. We also have a shortcut to solve such type of a problem, which is also a formula. X is equal to square root of q1 or square root of q2 minus square root of q1 whole twice L, where q2 is greater than q1. To verify this formula, again we consider we have the charges q1 is equal to q and q2 is equal to 9q, and after replacing these values in the formula, we have the relation x is equal to square root of q over square root of 9q minus square root of q whole twice L, and square root of q will cancel to the square root of q, and our relation will become x is equal to 1 by 2 whole twice L, which is a similar result to our previous problem. And thank you very much for watching my video. Please like, subscribe, and it is a motivation, for me to make better and better videos for you.